Continuing with the series on definite integration, today we are going to discuss the applications of definite integral in finding the area under the curve. Now, what do you understand by area, and that too area under the curve or bounded by a curve? Well, as a common and layman answers, it will come out as it is the portion that the curve or a particular region occupies on a plane. This graph represents a particular salesman's annual earning rate, and this graph is such an odd shaped figure, but still the area, that is this portion that is under this curve, represents the salesman's annual income. Now, if you have to find this area which represents his annual income, then there is absolutely no algebraic tool available with us. We have no formula which can tell you how to calculate this area. Calculus helps us here. Calculus helps us in finding such areas by inserting number of rectangles in between this region, and as the number of rectangles is increased, you can see here the difference between the total of the areas of the rectangle and that of the area under the curve reduces almost to 0. This is the technique which we call as the slicing and summing. We discussed it in great detail in our first lesson, and we discussed it and concluded there that this is exactly how the concept of definite integral was evolved. Take a look at the result which we had mentioned in our first lesson also. Here we have for you a graph of the function y equal to fx, where fx or y is a continuous function in the closed interval a to b, and then the area under this curve as shaded here, bounded by x-axis, that is important to note, is given by the definite integral a to b fx dx. And so, what you need to know is exactly the shape of the curve before you start with your calculations, and also you need to know the limits which one required to integrate the function within. So, for that you need to know certain important things about what we call as curve sketching. One of the important tools of curve sketching will always be the symmetry of the function. If the function is symmetrical, it will reduce our work by halves, or even it will reduce it to much more. Now, what we have as symmetrical functions is to remember that if your function has even powers of x, for example, if your function is y is equal to x square, then such a function will always be symmetrical with respect to the y axis. If there are even powers of y involved, then the function is said to be symmetrical with respect to the x axis. And so, every function which may, if I may just take a simple example like x is equal to y square, other than the symmetry, certain known figures that you had come across in 11th standard coordinate geometry will be of use. You must remember certain very important characteristics of standard forms of the parabola, and also forms of the parabola which are not in the standard form. Just a quick look as to what standard form means. You have y square equal to 4ax and you have x square equal to 4ay. They stand for the parabola, and as we just mentioned, the immediate equation gives you the value, gives you the image of the curve. You have y square, so the function is symmetric with respect to x axis. So, it should represent a parabola which is going to be symmetric with respect to x axis, and standard form means it is going to turn at the origin, and so our shape of the parabola will be like this. Whereas x square equal to 4ay will always be a curve which is symmetric with respect to the y axis, and being in the standard form, its vertex will be 0, 0. Other than parabolas, circles are going to be of great importance to us. You must always remember how to find the center and the radius of a circle, and exactly what and where the circle is going to place in terms of the axis. For example, again one very commonly used circle will be of the form x square plus y square equal to a square. And you all, I think, know that the center for such a circle is 0, 0, and the radius? Well, the radius is a. If I have another center, the equation will look like something like x minus h whole square plus y minus k whole square equal to r square. And let's see how definite integrals helps us in finding area of bounded regions. The first example is a very simple one. Find area of the circle x square plus y square equal to a square. So, you need to know and get an immediate picture as to what are we talking about. It's a circle, right? And it's a circle with the center, as I just discussed, as the center at the origin. So, it's 0, 0, and the radius of this circle is nothing but a. And so, a curve, that is a rough curve sketching, is required. Here we have for you the circle drawn as accurately as possible, and you have it center at 0, 0. Radius being a means it cuts the x-axis at a0, cuts the y-axis and 0a, and of course at these 2 points. Now, you can see that in this whole circle I have shaded only one region here. That's to reduce our work and also to use the concept of definite integrals here. You know by the symmetry that the total area of this circle is just 4 times the area of this sector. So, this sector is the region which is in the first quadrant, and so we can say it's bounded by the x-axis, and the region area is varying from this point up to x is equal to a. So, from x equal to 0 to x is equal to a, and the curve is given by, of course, x square plus y square equal to a square, but as a function as y in terms of x, it can always be written as y is equal to under root of a square minus x square. So, you know the limits and you know the function, and therefore, the area of circle will be 4 times the area of the region, I can say OAB, and that is equal to 4 times 0 to a, 0 to a because x varies from 0 to a in the sector shown, under root of a square minus x square, fx dx, here fx is root of a square minus x square. And now simple integration and check if it comes out to be the same as it should come by the simple knowledge of the formula for area. I'll leave that working for you. Now, what you must have gained out of this lesson, this question, is that the procedure involved here is very much a step-by-step procedure. A step-by-step procedure which requires in our sequence certain things to be done. Let's quickly take a look at to what the sequence and the steps require. The first thing that you must know is to make a rough sketch of the graph of the given function. That's what we did. We first draw the circle, mark the region whose area is required, and of course, use symmetry at this level to understand as to where you can save the work. Find limits of integration, and then the last, evaluate definite integral between the limits obtained in step number 3. If you keep these steps in mind, your work will become a very simple task. But as you will see, and you will definitely will come across situations where instead of finding area under the curve, we will be more interested in finding area enclosed between 2 curves. Now, what do we do in such a situation? Well, not too many complications come here, but what you can see from this figure is that if I have a curve y is equal to fx and I have another curve y is equal to gx intersecting, and I want to find the area enclosed between these two from x is equal to a to x is equal to b, then what I can do is take the area under the curve fx, subtract this portion which is the area under gx, and we will be left with this shaded region, and that is exactly what we have as the result. Area enclosed between y is equal to fx and y is equal to gx is given as a to b fx minus gx and just an integral of it. So, you have integral a to b fx minus gx, and you get the area enclosed between the curve y is equal to fx and y is equal to gx. It sounds simple, it works also quite simply if we use it in the right fashion. Now, what you also have to note here is that in addition to the steps shown earlier, you have to add one more step, and that is to find the limits of integration. You should know the points of intersection, point or points of intersection as may come in this particular example, and they will give us the limits for integration. So, let us consider one example on the same situation and note the question carefully. We have the question as find the area enclosed between the curves y is equal to half x square plus 1 and the line y is equal to x plus 1. So, what we have here is y is equal to half x square plus 1. What kind of a function does it represent? Right, the curve is a parabola. And of course, before drawing the sketch, always make your first point in the step required as the point of intersection. And point of intersection is nothing but the common solution of the two equations. So, you just have to solve them simultaneously, and that we can do very easily here by writing it as half x square plus 1 is equal to x plus 1, and that gives you either x is equal to 0 or x is equal to 2. Do not ignore this possibility, do not cancel an x directly and just write x is equal to 2. That will be totally wrong, because it is going to be of great importance to us. And so, we can say that the points of intersection comes out to be as an ordered pair. When you put x is equal to 0, y is equal to 1. When you put x is equal to 2, y is equal to 3. So, the common point between the two curves are 0, 1, 2, 3. They are the points which are going to give you the shape of the curves as well as the region to be plotted. Now, keep in mind you have half x square plus 1. So, it is a parabola, but not in the standard form. Its vertex can be calculated, and the vertex comes out to be 0, 1. For that, you may either reduce it to the standard form, or now even I will suggest that since you are experts in finding derivatives, you can use the concept of differentiation. This is a shape, a U-shaped curve, where this is the point of minima, and so you can take dy by dx of the function and put it equal to 0, and you can find and use the concept of local maxima minima to find the point where the curve is going to turn. So, you have 0, 1 as the vertex, and you have 2, 3 as the point which the two line and the curve share. Y is equal to half x square plus 1 means it is symmetric with respect to the y axis. Knowing this, one can draw the sketch, and then the region or area enclosed between the two can be definitely taken to be this, and this area is nothing but, again keeping in mind that you know how to find area under the line. So, it is area under the line from which point x is equal to 0 to x is equal to 2 minus the area under the arc AB, again from the point 0 to 2. So, what I can say here is, if I may just write the point P and Q here to keep a distinction, you can say the required area will be equal to area APB, area under line APB minus area under arc AQB. You can see that again. You have area under the line APB minus area under the arc AQB, and that is equal to The limits as shown earlier will be from 0 to 2. APB is defined by the line. So, y is x plus 1 minus arc AQB is defined by y is equal to half x square plus 1, and the limits are again the same as y is equal to half x square plus 1, and you have the limit same as 0 to 2. This is what you have as the required area, the difference of these two integrals. Solve it and see that it comes out to be equal to 2 by 3. Integration in fact is the most trivial thing. What is very important is the identification of the region and the correct identification of the limits involved in the calculation. Let us consider one more situation where there is going to be a twist in the way that we are going to use area enclosed. The question says, find the area enclosed between the circles x square plus y square equal to 1 and x minus 1 whole square plus y square equal to 1. We have a situation where both are circles. The first one has the center at right origin and the radius is 1 unit. What about the second one? Center exactly x minus h, so it is 1 comma 0 and the radius again 1. So, when you draw the sketch, your circles should look like as they are going to satisfy the conditions, and they will look like this. Again, what is important is the point of intersection. So, solving the two equations simultaneously, you will have the point of intersection coming out as half and corresponding value of y as root 3 by 2. You will have also the corresponding value here as x is equal to half and y is equal to minus root 3 by 2. Now, I have shaded the region here, but you can see that the total area required is twice the area in the first quadrant. So, the area required is actually twice the area OAB, and that is how we are going to do our work. If the required area is equal to twice the area OAB, so we will now concentrate on finding the area OAB. For that, you again need to take a good look at your curve. Area OAB is not the difference of the two areas as we saw in the previous case. Here, in fact, from O to A, the curve is decided and defined by the equation x minus 1 whole square plus y square equal to 1. That is the second circle shown in green here. Whereas from A to B, the boundary changes and it is defined by x square plus y square equal to 1. And the total area is the sum of these two portions. So, if I divide it at the point P, what I can say is that the area OAB is same as area OAP plus area PAB. And now there will be no trouble because this area OAP is from 0 to the point of intersection and the x coordinate only of that is required. So, you have from 0 to half under root of, you have the function OAP given by the circle with the center 1 comma 0. So, it will be 1 minus x minus 1 whole square plus, now again a change here, the area PAB comes from this line to the ordinate constructed at point B. So, it is x is equal to half to x is equal to 1, and the limits will be from half to 1 and the function is 1 minus x square in the square root. And this is how you will get your total area required. I will leave the integration for you. You must be an expert in that by now, and check whether you get your answer as 2 pi by 3 minus root 3 by 2. Now, in the forms of the different questions, there is one very interesting and very specific form that you will always come across, and that is of the area bounded by a triangle, which of course you have learned now by in so many ways. You know how to use determinants, you know how to use coordinate geometry only. But if the question says using integration, find the area of triangle ABC whose vertices are given to you as -1, 1, 0, 5, 3, 2, then it means we have to bring in definite integration. So, first thing that we will do is we will form the equations of the sides which represents the sides of the triangle, and that is done by using 2-point form. So, no new concept involved here. Find the equations by taking the y minus y1 is equal to mx minus x1. I have the equations here, so you can note them down, and you can see I have separated y. I want to integrate y with respect to x, so I have written y in terms of x. You also can do that, and it will make the task easier. And the next step is to plot and get the shape. When you plot the points, you will have your triangle in a position like this. And here at this stage, it must be made sure that you write the equation which represents the sides. So, you have y is equal to 4x plus 5 representing AB, AC is represented by y is equal to 1 by 4 x plus 5, and BC is represented by y is equal to 5 minus x. To find the area of the triangle ABC, what will we do? Take a look. Area of the triangle ABC can be thought of as area under the line AB from x is equal to -1 to x is equal to 0 plus area under BC from x is equal to 0 to x is equal to 3, but that brings in certain extra area. So, subtract the area under AC from -1 to 3. That is exactly what we are going to do, and there is no hard and fast rule for such situations. You will have to draw the curve, and then only you can decide which areas have to be added and what has to be subtracted. So, in this case, area of the triangle ABC can be taken as area under AB plus area under BC minus area under AC as shown, and this is equal to AB, the coordinate, the limits comes from -1 to 0 and function is 4x plus 5 plus 0 to 3 5 minus x dx, and what do we have to subtract? The area under AC. So, the limits for A and C starts from -1 to 3 and 1 by 4 of x plus 5. It is a very simple integration now. So, you will do that task and check. The answer should come out to be 15 by 2, and of course, you can always write square units here, which I did not do in the last one, but the square units is always the unit for the areas. And of course, you can always check your question by using the determinants. This question can also be, and is always, you will find in all the books, framed as the equations being given, you have to find the area. The only change comes in that situation is to find the point of intersection, solve the equations pairwise, and you will have the points A, B, C, and then the work remains just as we discussed here. Now, instead of asking you to find the area enclosed between two curves, if the question says find the area of the region given as x comma y such that x square plus y square is less than or equal to 2ax and y square is greater than or equal to ax, x and y are both greater than or equal to 0. We proceed exactly in the same fashion as we did earlier with just a slight change. So, the first thing still remains to find the point of intersections, and here just take the equations instead of inequations. Solving them simultaneously, you can show that the point of intersection comes out as 0, 0, A and A minus A. Also keeping in mind that this here is a circle with the center A comma 0 and the radius A. It passes through the origin also. So, its shape will look like a circle with the center A comma 0. Y square equal to AX is a parabola symmetric with respect to x axis. So, drawing just the equations, we have the two curves plotted. What you have to identify now is the region, and to do that you have to use the inequations here. We have x square plus y square is less than equal to 2ax. Now, the circle has two regions in this particular plane, one inside the circle, the other outside. Take the point A comma 0. Check, does it satisfy the inequation x square plus y square is less than equal to 2ax. Put x is equal to a, y is equal to 0, and if it satisfies, which it does, the area will be inside the circle. Whereas for the parabola, you have the inequation as y square is less than equal to, greater than equal to, ax. Take again one point which is either inside the parabola or outside the parabola. Here if we continue with the point a comma 0, does it satisfy this? Well, certainly not. 0 is not greater than a square. So, the region for the parabola inequation will be outside the parabola, and so the common portion will be where the two cross each other, where you get a checked portion. But you have to be careful before you shade this portion, because we also have a restriction of xy greater than equal to 0. So, our area is only in the first quadrant. Had it been that condition not being there, you can always take the area under this, and by symmetry it will be the double of the area in the first. So, the required area we have as area under the circle OPA minus under the parabola given by arc OQA. Do we get that? So, this shaded portion, that is area OPAQ, is calculated as the difference of the two areas, and so we can write the required area to be 0 to a. The limits again come from the point of intersections. So, 0 to a under root 2ax minus x square with respect to x minus 0 to a under root ax, the y function which defines the parabola. Calculate this as you need to do for the integration, and then check if your answer comes out to be pi a square by 4 minus 2a square by 3. The procedure is same, but identification of region is a must. Now, every question that we have discussed so far, we have stayed in the first quadrant. We have tried to find the area bounded by the x-axis. Now, what happens if the curve goes below the x-axis and there is no symmetry? So, you can't use the symmetry to double the area or take 4 times the area and use the area under the curve as discussed earlier. Well, still we can use it. See the situation here. We have a curve PQ giving you the function y is equal to fx. So, if you have a situation like this where the curve is below the x-axis, what you need to do is take its image across the x-axis, and when you take its image, the function changes to negative fx, and the area APQB as shown here comes out to be a to b minus of fx dx. So, that is the only thing you have to keep in mind. Let us see a question and see how it works. Find the area enclosed between the curve y is equal to 4x into x minus 1 into x minus 2 and the x-axis. So, first thing is the plotting of the curve. Now, this function as it was given can be always thought of as a function which can be reduced to a cubic polynomial. So, it is very much a polynomial function. To get this shape which I have ready made here for you, you only have to observe that the curve cuts the x-axis when x is 0, that is when is y 0, when x is 0, x is 1, x is 2. So, the curve cuts between these 3 points. Also, how do we know it is going to go like this? Again, you just have to keep in mind that between 0 to 1, the function takes the positive value. So, the curve has to be above the x-axis, and when you take the point between 1 and 2, the curve has to dip down. There is no symmetry, and therefore, it has to be something like which has to be calculated independent of each other. So, the total required area is actually the area I1 plus area I2. I1 is no trouble, I2 is now no trouble, because we know we can find its area by taking negative of the function involved, and therefore, we can write the required area to be I1 plus I2, where I1 is 0 to 1, 4x cube minus 12x square plus 8x, since between origin to A, the function takes the value as the positive. So, from 0 to 1, you have the same function. I2 will vary from 1 to 2, x is equal to 1 to x is equal to 2, and the function is taken with a negative sign. And integrating, solving it out, check if the answer comes out to be a simple 2. So, we have taken number of cases. You take more questions and get the idea and the concept absolutely clear. Thank you.